Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
Welcome back, everyone. This is part 2 of week 4, and we are about to dig into some seriously cool stuff. Last time, we saw how AlexNet basically kicked down the door for deep learning. Today, we're going to look at what happened next, the brilliant ideas and the mathematical wizardry that took us from just a few layers to the absolute monsters we have today, networks with hundreds of layers.
All right, so let's set the stage. The story of modern CNNs is really a story about hitting a wall and then finding a super clever way to get around it. You see, the first idea was simple. Just make it deeper, stack more layers. But that brute force approach, which you see with VGG, quickly ran into some major problems. We're going to break down those exact bottlenecks and explore the elegant solutions that completely changed the game.
And that wall we just mentioned? It pretty much had a name, VGG. This network was really the peak of that bigger is always better philosophy. And look, it was a beast for sure, but it also showed everyone that this approach was hitting a dead end. Just stacking more and more of the same old layers wasn't just getting inefficient, it was becoming a serious roadblock to making any real progress.
And this chart right here, it just lays the problem bare. I mean, look at that jump in parameters from AlexNet to VGG11. We're not talking a little bump. It more than doubled to 133 million parameters. And you can see the culprit highlighted right there. It's those fully connected layers at the end of the network. They were an absolute memory and parameter hog.
Yeah, this wasn't just some abstract issue on a whiteboard. It was a practical nightmare. These dense layers took up a ton of memory. They were super slow to train. And maybe the worst part is they just took all that valuable spatial information that the convolutional layers worked so hard to extract and flattened it, threw it all away. So the challenge was crystal clear. How do we get deeper without this crushing computational weight?
Well, this challenge is what kicked off an efficiency revolution. The whole goal shifted. It wasn't about raw power anymore. It was about being architecturally intelligent. Researchers started hunting for ways to get the same performance, or, even better, but with just a fraction of the computational cost.
And one of the most elegant tools they came up with was the one-by-one convolution. Now, it sounds almost too simple, but this thing is an absolute powerhouse. The best way to think about it is like a tiny, fully connected network that just looks at one pixel at a time, but across all its channels. Its genius is that it lets the network mix information across those channels, like a feature blender, without changing the height or width of the image at all.
And this slide right here shows the real magic of the one-by-one convolution in action, using it as a bottleneck. So before you do a really expensive 3x3 or 5x5 convolution, you first use a cheap one-by-one convolution to squeeze down the number of channels. The result, as you can see from the math, you get a staggering 10x reduction in computation. This one little trick was a total game changer, and it's what allows us to have powerful models running right on our phones today.
Okay, so the one-by-one convolution helped clean up the middle of the network. But what about those monster dense layers at the very end? Well, for that, we got another brilliant idea, global average pooling, or GAP. Instead of flattening that last feature map and connecting it to millions of parameters, GAP just takes the average of each feature map. That's it. And then it feeds those averages to the final output. The result is just incredible. 0 new parameters. It was a simple, radical, and hugely effective solution.
So let's see how these pieces come together. This is GoogLeNet's famous Inception block. And honestly, this thing is a work of art. It's designed to look for features at multiple different scales all at the same time, using different size convolutions, even pooling, all in parallel. And the only reason this complex beast is even possible without, completely melting your computer is because of those clever one-by-one convolution bottlenecks that keep the computational cost under control.
Okay, so with these powerful new building blocks, the race was on to build deeper and deeper networks. But as people started pushing past 20, then 30 layers, they realized architectural efficiency wasn't the only problem. A totally different issue started popping up, something that made the whole training process unstable and just plain chaotic.
And this is a fantastic way to visualize that problem. It's called internal covariate shift. Basically, as the weights in the early layers of the network get updated, the distribution of the data going into the later layers is constantly changing. It's like trying to learn while the rules of the game are changing every second. You get this messy, chaotic optimization landscape on the left. Batch normalization fixes this. It basically recenters and rescales the inputs at each layer, creating that beautiful, smooth landscape you see on the right, which is so much easier for the optimizer to navigate.
So how does batch norm actually work? Well, it's a pretty straightforward four-step dance. First, for any batch of data, it calculates the mean and the variance. Then, it uses those to normalize the activations. But here, this is the really clever part, it then uses two learnable parameters, usually called gamma and beta, to scale and shift that normalized output. This is crucial because it gives the network the flexibility to undo the normalization if it decides that's better for learning. It gets the best of both worlds, stable training and full expressive power.
All right, so now we've got efficient building blocks and stable training. We've solved all the problems, right? We should be able to build networks that are thousands of layers deep with no issues. But the story has one more really surprising twist.
So I'll just ask you directly, with all these tools in our toolbox, can we finally just stack layers to our heart's content and expect the performance to just keep getting better and better and better?
And the answer, which shocked everybody, was no. Researchers found this bizarre phenomenon where a deeper 56-layer network actually had a higher training error than a shallower 20-layer network. And let me be clear, this was not overfitting. The error on the training data itself was worse. This was a pure optimization failure. The signal, the gradient, was getting so weak on its long journey back through the network that the early layers just weren't learning anything meaningful. They were effectively frozen.
The solution to this was just so elegant. It's called residual learning, and it's the core idea behind ResNet. The idea is this: instead of forcing a stack of layers to learn some perfect, complex transformation, let's make its job easier. Let's just have it learn the difference, the residual, between what it should output and what it started with. Then, we add the original input X back in using this special skip connection. It turns out it's way easier for a network to learn to do nothing or make a small change than it is to learn a perfect copy from scratch.
And this slide right here shows the secret sauce. It's just a beautiful bit of math. That simple skip connection does something magical when you calculate the gradients. It creates this +1 term in the chain rule, and that +1 acts like a gradient superhighway, a pristine channel that allows the error signal to flow all the way back to the early layers, completely unhindered. This simple little addition is what finally smashed the depth barrier and paved the way for the ultra-deep networks that we have today. It's just genius.
So these three big innovations, efficiency with one-by-one convolutions, stability with batch norm, and incredible depth with these residual connections, they didn't just solve their own little problems. They all came together to form an entirely new blueprint for how you design a modern high-performance CNN.
And this is basically that blueprint. A modern network usually has three distinct parts. You've got a stem, right at the beginning, that quickly gets the input down to a manageable size. Then you have the body, and this is where all the heavy lifting happens, made up of stacks of those efficient blocks, like Inception or ResNet blocks. And finally, you have the head, which uses something clean like global average pooling to make the final prediction. This modular, stem, body head design became the new gold standard. So let's just take a quick step back and appreciate this whole journey. We started in the age of brute force with VGG. Then we had the efficiency revolution, kicked off by ideas in networks like NIN and fully realized in GoogLeNet, which gave us these amazing tools like one-by-one convolutions and multi-scale blocks. And finally, ResNet came along and just solved the whole depth puzzle with its beautiful residual connections, which pretty much became the default architecture for almost everything.
So if there's one thing you take away from all this, it's this. The story of modern CNNs isn't really about just getting deeper. It's about the clever, mathematically solid designs that made that depth both possible and practical, all by focusing on two things: making sure the gradient can flow and being computationally efficient.
And that brings us to one final really important thought. We now have these amazing blueprints to build and train incredibly powerful networks on massive datasets. But doing that takes a huge amount of data, a huge amount of time, and a huge amount of computer power. So is there a way we can leverage all that hard work without having to start from zero for every single new problem we face?
Well, there is, and that idea is exactly what we're going to cover in the next part of this lecture, transfer learning. Thanks for watching, and I'll see you in the next one.